Hello everybody and welcome to another video. Today I wanted to talk about a very interesting topic uh, that a lot of programmers seems to miss, especially the beginners. And my motivation for this video primarily is for many posts on Stack Overflow where people come up saying Python is faster than C++ or JavaScript is faster than C++ and stuff like that. Now, there is a lot, well, not a lot, but we have to first understand our perspective and try to break down why is Python code, for example, faster than C++, because how in the world is an interpreted programming language that executes at runtime in its own virtual machine faster than something that's executed natively on my machine? So when you look at Python, everything written in Python will go through its virtual machine at runtime. So the only optimizations that Python can make is at the bytecode level. First, when we write a Python program, the Python software needs to translate it into bytecode for lightning speed execution. And then in the middle does a lot of optimizations that are kind of similar to what GCC does for its assembly output. It's similar, but it's not the same because bytecode of Python is kind of similar. It can be similar to Java bytecode and stuff like that. So it is not essentially assembly, but it is trying to be assembly for your virtual machine implementation. So I wanted to look at one specific function that I built a while ago in Cython. Well, first I built it in Python, and then in Cython, and then C. Why did I do this? In Python, there's a split string function. It does something like this, right? You have your string and then you simply split it. Split. And what it essentially does is that it takes the delimiter and splits your string as appropriate. There are a lot of use cases for this, especially resplit when it comes to parsing URLs and anything like that. Or if you have a record from the user that inputs, let's say, an array like this, and you want to make sure to split all of the white space, or just space. If you want to do all the white space, you would use regular expression split, where you get the output. So I picked this simple function to demonstrate that you can build really fast functions. And if you want to accomplish that, you wouldn't build them in C natively. In Python natively. Let me show you this example of a benchmark test. Where let me just build that, and I do Python quick. Is it quick? Yeah. So Python, if we look at the split function written in native Python, there are a lot of overheads that take place. For example, in Python, every single reference or variable is not just statically declared, right? So there is no Python runtime virtual machine has to go through a check to see if this variable, what is this variable? Is it a number? Is it a function? Is it a string? So it does quite a good job at optimizing that, but at the same time, there's still that determination. Well, not determination, but there's still that, well, it is to determine what is our next step. And also because this function is interpreted by the Python interpreter and virtual machine, it's never gonna run as fast as something written in C. And you may be wondering, why is the built-in split of Python so freaking fast? Isn't it written in Python? Well, it is not. And that is because for performance purposes, it is built in C. So there are no, and as you already know, Python is implemented in C. So you can export your functions onto C and call them from Python. I also tried implementing this function in Cython. While it is faster than native Python, it is not our peak performance. And also, if you look at the NumPy implementation of the split, you'll see that, okay, this is pretty fast as well. How are they that fast? Well, they also use C, right? And to show you this implementation, there will be no overheads. The function will be called as a dynamically compiled and linked function that you would typically do from C or C++. That's why there is no overhead. If we go to the Python code base, we'll see split function. And this function is exported onto the Python environment where it will run it natively 100%. Although there will be one overhead, which is the function call, because dynamically linked functions from, I don't know, dynamic link libraries, they cannot be inlined, obviously. Needless to say, so there are no optimizations that you can make when you call a function. You will always have to first resolve it at runtime, and that's how dynamic linking works. We can cover that in another video. And it's just, the point is, it's all at runtime. So that's probably the only overhead you're gonna have. Everything else is gonna be purely C. There's no overhead whether we're checking which type is which type. We're calling straight objects, and we are using something called Python C API in order to convert C-like types to Python, to respective Python types. While in the body of the call, we primarily use C specific types because of the performance. And that's the whole point, the performance. And that is why built-in functions and any functions written in C will always be faster than Python. And if you want to build really fast stuff, use C, and there you go. And I'll show you the example of that in my own split. So I've taken the Python C API and I wrote everything in C so I can reach my peak performance. Now this code can be a little improved. You don't want to see long kind of stuff in here, although it will work for every machine nowadays because it's all 64 bit. But yeah, I gotta be cautious about this stuff. This is all very experimental anyway. It's just trying. I was just trying to experiment and build my own function. So once I build this and write this into C, I export it via Cython because it's the easiest way. You just do extern from here. CDEF allows you to do that, and then you just reference them via their declaration, and you just export them for Python. And that's essentially how it works. If we look at our very brief benchmarks here, we'll see that Python split still performs better than our own PySplit. And I also created a split function that uses the same algorithm in C++. So I also benchmarked that, and our performance is not particularly great compared to C, because there are a lot of improvements we can make in the C++ algorithm and whatnot. So to get back to our initial point, why is my C implementation faster than C++? Well, it's the algorithm after all. Or why is built-in function of Python in an interpreted language faster than something I wrote in C++? You gotta say, is the algorithm, because we've broken down, we've gotten to the bottom line, right? And that is, are we executing bytecode? No. Are we executing Python? Are we executing C when we first dynamically compile it? Yes. So we take the C implementation, turn it into C++, and that's how we get it. We try to get the peak performance. And that's where we can see why Python will be faster than C++, and that gives us to the bottom line. If we've come to the lowest level of implementations, in the end, it is our algorithm. So, if we look at the Python implementation of split, they use a combination of Boyer and Moore and Horspool algorithm, whereas we use just the linear function string find methods, and they don't come close to Boyer and Moore algorithm. And I'll show you a graph where we've actually beaten the NumPy implementation, by the way. And this is also available as part of my library here. You can draw your benchmark diagram to check out who performs the best, which function performs the best here. And we've definitely beaten the NumPy, I would say. And where our separator is this. Now I will try to run or build my graph where we perform against the built-in function. So the built-in function will always be faster because the algorithm is faster, since we've gotten to the lowest level of implementation. And I'll try some others. So this is when your delimiter cannot be found. I will try adding something else, whereas my delimiter or separator, let's say it would be just double space. And now we are trying to kind of fight with the built-in function, but still we're not getting there. Now if we try to, I don't believe I have that, test as pi. Yeah, let's try to call a native Python function that we built in Python compared to our C implementation, and not the built-in Python implementation. It's our function here, sisplit. So where is that? Pi.split s.delimiter. That should be that. I haven't checked this. Okay, let me just verify how to call my home function. PySplit, alright. PySplit, oh, of course, is the underscore, right? And now if we check the benchmark for 1 second, plot, I want to plot PySplit. See if that works. Okay. So here's the difference. Here's our C implementation, C level implementation, and here's our Python native implementation, which is just nuts. I think you get the point of this video, and probably the only confusing point about this is how is C++ function slower than C function that we implemented? That can be a lot of things that can be considered. One is that the vector that the built-in array in Python performs reallocations better or more efficient, and we can try that, by the way, by saying array dot reserve, and I'll just reserve about, what's my threshold here, 100,000. Okay, let's go with 100,000, but this is sort of, it is predefined after all. Let's see how much we're gonna get, how improved. Yeah, here it is. It's those small things that come into consideration, and we've definitely finally gotten what we want to get in terms of C++ results. So now we cleared that confusion for sure. Now it's definitely similar with our C implementation. And these are the kind of things in C++ that are very, very fragile, and you gotta be really careful with your implementations. I also have an implementation where I don't use a vector, I use a stack. And stack is much faster. Let's try to do that, by the way. I'm just very curious right now. Buffer container. I believe this is it. We're gonna get some errors because there's no pushback. I don't remember what is the where's the function for the stack that does that? Is it push? Oh, okay, it's just push. So let's do the push, shall we? Let's do the push. Now reserve. We cannot reserve a stack. Where's my reservation? Okay, I get it. Let me just push it here as well. We built two separate functions because they will perform differently. The first function is a split function where we have a delimiter that's a string and a delimiter where we have a character. Because now we can have a very, very advanced boost where instead of this logic where we have an if for, because a string is just more than a one in length, in size, and whereas character will always be one character, so we don't have that kind of overhead. And I'm just stuck at the moment. Let me just check out the reference for a stack in C++. In place, stop, swap. Wait, there's no reserve? Maybe the capacity I can find. Reserve. Oh, it doesn't seem we can reserve a stack anyway. Let's check the performance then. Now our performance is really sky high, which is awesome. And that's how you make, when you get to the lowest level of implementations, that's how you make your C++ implementations faster than the ones in Python. Even if they're written in C, you can still perform better. In some cases, even though we said that all Python built-in functions are built at the same level. At the low level, actually. So you can most certainly perform better because Python relies on its C API, and that C API is not really, it's still dynamic. It's still really dynamic because Python object can be a string, can be a union, not a union, can be a string, can be a number, and stuff like that. And all of its stuff, it's allocated on heap, whereas you can have those overheads removed depending on your C++ implementation. So let me just wrap it up by comparing these two screens, and there we go. Anyways, thank you so much for watching. And I mean, there is still this improvement that we can do here because Python built-in function is still faster, but like I said, it is always the algorithm once you get to the right level of implementation. Thanks so much for watching the video and take care. Bye bye.